And welcome to another video on tolerance stackup analysis. In this video, we'll be dealing with a GD&T based drawing of two parts of part A and part B, which are assembled as shown. And over here, we need to find out whether the pin, which is shown over here with the dimension 4.5 plus or minus 0.1, will it be able to pass through the hole on this assembly in the worst case. Considering we have GD&T drawings for part A and part B, and this bottom surface is considered the datum surface for part A, the prime datum surface for part A, and then the axis of the hole on part B is varying with respect to this bottom surface of part B, and which in turn is varying with respect to bottom surface of part A. So there is a tolerance change which is getting created over here, which we will see as we go through the drawing. The main aim is to calculate whether the pin of 4.5 plus or minus 0.1 will pass through this hole or not. So first variation which we will consider is the variation in the orientation of the top surface of part A, which is shown over here. That is variation number 1. Variation number 2 will be the change in orientation of the axis of the hole on part B, and the third variation will be the change in orientation of the axis of the hole on part A, which is this one, the small hole. So there are three major factors which come into play, which will govern whether this pin we will be able to insert this pin into the hole or not. First is orientation of part A top surface, orientation of hole on part B, orientation of hole on part A. Over here, for simplicity's sake, we will consider the position and profile deviations as negligible as compared to orientation, because here the main focus is the deviation of orientation and how that affects the assembly. So we are going to focus only on that, and we are going to factor in only the orientation deviations and how that affects the assembly, because that will be the most influential effect in the assembly of this pin through the part A and part B stacked. Now let's have a look at the GD&T drawings for part A and part B. The part A is the sand color part, the base block. So the primary datum feature is denoted as P, which is the bottom surface, and there is a profile control attached on this surface on which the part B is rested. And the profile control basically controls two things. One is the size of width of this block, the position of the surface, and basically it is controlling the orientation of the surface as well within a tolerance zone of 0.2 with respect to P. And there is also another orientation control for the hole. So the parallelism of the hole is being controlled within a cylindrical tolerance zone of 0.2 with respect to datum feature P, which is this primary datum feature, and the size of the hole is 6 plus or minus 0.1. The width is 6 plus or minus 0.1 for this, and the total width is 60 plus or minus 0.2, and this is the basic dimension for this profile control, and this 24 is the basic dimension for the orientation control. Here is part B, which is the pink color part. So bottom surface is datum feature A, primary datum feature bottom surface, and datum feature B is the width of the part, the feature of size 17 plus or minus 0.2, and datum feature C is this end surface. So the total length is 45 plus or minus 0.2, and the position of the hole is being controlled within a cylindrical tolerance zone of 0.2 with respect to datum A, B, C, and the size of the hole is 5 plus or minus 0.1, and the basic dimension is 14 from datum feature A, which is controlling its vertical position and orientation. So the position control of this hole automatically controls the orientation as well. So position means that orientation and position are being controlled, and since we are considering negligible position deviation, we are only focusing on the orientation deviation. Now let's calculate the first form of angular deviation, which is the orientation of the part A top surface, which is this surface. So there is a profile control which has been applied, which means that there is a tolerance zone of width 0.2 located over here. And since we are considering only orientation, these are the lines which are denoting the worst case orientation of the surface. So it can be oriented like this or it can be oriented like this. So that orientation, what is the extent or what is the angle, maximum angle it can change its orientation to, can be calculated using the tolerance zone definition. So the tolerance zone is defined based on the distance from this point to this point, which can be calculated using basic tolerance stackup of 6 and 60, which is 60 minus 6 is 54, and plus or minus 0.1 and plus or minus 0.2 gets added, so plus or minus 0.3. So 54 plus or minus 0.3 is the specification for the distance from this point to this point. So from that, the worst angular deviation will be when the distance is smallest, when the tolerance zone is the smallest. So highest angular deviation will be when the tolerance zone is smallest in its width, which is 54 minus 0.3, which is 53.7. From that, we can take the right angle triangle from this and calculate the angle. So 0.2 is the width, or is the side of the right angle triangle, and the other side of the right angle triangle is 53.7, and the hypotenuse is this one. So using the adjacent and opposite, we can calculate the angle, which is 0.2134. So theta 1 is plus or minus 0.2134. This is the angular deviation of the surface because of this profile control which has been applied. The next source of variation is the orientation of hole on part B. So this hole will vary in its axis as shown. So this is the tolerance zone with the yellow boundary. It is an exaggerated tolerance zone. Of course, it will not be as big, but it is just to show the variation of the axis, as it will vary in its orientation with respect to datum feature A, which is the bottom surface of the part B. And this datum feature A is being rested on the top surface of part A. Hence, the orientation changes of that surface will get carried over to the bottom surface of the part B. Hence, it will be an angular stack up. So the angle can be calculated similarly. We can take the right angle triangle again, similar. 0.2 is the opposite side and adjacent side is 44.8. So this distance is calculated using this value, 45 plus or minus 0.2, the width of the part, which is, we are considering the highest angle deviation is in the smallest tolerance zone. So 44.8. So we can calculate the angle. Opposite is 0.2, adjacent is 44.8 using tan theta formula. Tan theta is equal to opposite by adjacent, 0.2 by 44.8, and then finding the tan inverse, we will get theta 0.256 degrees. So theta 2 is plus or minus 0.256 degrees, which is the second source of variation. Now the next step is to calculate the total angle. So the total angle we can calculate. So we are considering the master reference as the base surface of part A, and from that the angular deviation of the axis of the hole will be addition of theta 1 and theta 2. So theta 1 is 0.2134 and theta 2 is 0.256. So theta t, that is total angle deviation, will plus or minus 0.469 degrees. So we have calculated the total angular deviation which can occur for the long hole. Now for the short hole, which is larger one, we can calculate the orientation deviation which will occur because of the control which has been applied in the drawing. So parallelism control has been applied with a tolerance zone of 0.2. Hence, using the same method, using the right angle triangle, 0.2 is this opposite. This adjacent is nothing but the smallest tolerance zone size, which is 6 plus or minus 0.1, which means that it is 5.9. So 5.9 is the smallest tolerance zone. 0.2 is opposite, 5.9 is adjacent. Theta 3 can be calculated using this, and the value of theta 3 comes up to plus or minus 1.942 degrees. Now the next step is to do the envelope analysis with the angles which we have got, and to find out whether the pin 4.5 plus or minus 0.1, whether we will be able to assemble it in the worst case. So considering the worst case, we are considering the size of 4.6, which is the largest size of the pin. Whether that pin will be, we will be able to insert it into the assembly or not. So this is the assembly cut section view. This is the base reference. Now, considering the orientation deviation of the holes will turn out to be something like this. So this is the hole which has been oriented to its extreme on the part A, and on part B the long hole also has been oriented to its extreme as shown. So these are extreme orientations of the hole, and considering that this pin has to go through, so this pin, or this is an envelope which passes through the cavity of the hole 1 and hole 2 cleanly, and it assembles without any obstruction. This is called an envelope. So this is the envelope required for the assembly of any pin which goes through the two holes. So we need to calculate this size of envelope, which is the maximum size of pin which can be inserted into both the holes on part A and part B in the assembly. So that is what we need to calculate. We need to calculate the size of this envelope. We can calculate that by calculating the distance from this point to this point. Considering that the hole on the part A is larger and the cavity or the envelope for the part A hole is much larger, we do not consider that to be worst case. The worst case is the hole on part B, which is the longer hole, and the one which has the smaller dia. Hence that has to be considered for making the final envelope for the pin insertion. So this angular deviation is nothing but the total angle theta t, which is 0.469. Because this 0.469 is because of the deviation of this surface and also the deviation of the whole axis. So it is a stacked up angle, which is 0.469, and we can calculate what is the diameter of pin required by analyzing the geometry. So this is the pin and this is the hole, inclined hole, and the size of this, this is the envelope and this is the hole, and we need to find the size of the envelope. So for that we can find out the distance between this point and this point. Over here the distance between this point and this point can be found out by using the right angle triangle. Because they are alternate angles, this angle will also be 0.469. So we are considering the distance to be 44.8, that is the worst case, and we are calculating x, which is the opposite side. Here the opposite side is not known, we are calculating it based on the angle theta t. Earlier the opposite side was known, we were calculating the angle theta. Here we have known angle theta and we are having known adjacent, we are calculating the opposite side x. So using the same formula, finding the opposite side x, we will get 0.37 mm. Hence the envelope size will be nothing but the 0.37 subtracted from the smallest size of hole on the part B, which is the long hole. So the envelope size will be 4.9, which is 5 minus 0.1. The 5 is the nominal size of the hole on part B, which is the long hole, and minus 0.1 is the smallest size of the hole. So envelope size will be 4.9 minus 0.37, which is 4.53 mm. So the largest size of pin which can be inserted is 4.53 mm. And if you compare this 4.53 mm to this over here, we can see that in worst case the largest size is 4.6. Hence the pin will not assemble in this condition considering the worst case angular stack-up. We can calculate the envelope for the small hole as well, that is a shorter hole, the one with the larger diameter. The envelope size is nothing but 5.9 minus 0.2. This distance is 0.2, 5.9 minus 0.2 is 5.7. So this envelope is bigger, this envelope is smaller. The worst case is the smaller envelope, which impedes the assembly of the pin. Important disclaimer over here again is considering that there is no variation in the position of the holes and the location of the surface. The max size of pin required is 4.53 mm. So the answer to this question is whether the pin will pass through in worst case is that no, it will not pass through in the worst case. The specification should be changed. It should be 4.4 plus or minus 0.1 so that its largest size is 4.5, and whereas over here the largest size is 4.6, which impedes the envelope.